example, or if you were using C++, you read from C in, and then you write to system.out, cout, console.out, whatever language you're using. Your program does not open or close files, it just reads from system in. And the second one is, notice that 1.5, you're analyzing the algorithm that you're using for problem 1.4. That does not mean time the main method. Right? I don't want you to time how long it takes to do input-output. I want you to time it, write me a method that takes a list of words as a parameter and does what it's supposed to do. Time that. If you're timing the time it takes to input and output, that will dwarf the time it takes to do anything else. So just time the algorithm as we discussed it. It might require rearrange your implementation for Caddis a little bit. Yes?
Is it possible to turn off that light that's right above the projector?
Yeah, I'll turn it off when I really use the slides for real. Yep.
Did you put your slides on Canvas today?
Did I put my slides on Canvas? I believe so. They're the same ones we were using last time.
Oh, the same ones? Okay, then never mind.
Yeah, they're good.
Okay.
Yeah.
I noticed when I was timing my algorithm that when I was within that range from like 1 to 10,000 for the anagram problem that was on Caddis, it would actually be really slow because I could never time it over 1 second because each iteration was like under 1 millisecond. So I had to time, and it had to be over like 10,000. That was
No, okay, so you're saying that when n is small, n's an input to your algorithm.
Yeah.
It only runs for less than a millisecond.
Yeah.
So you do what I did in my example. You run it a bunch of times and average. You write a loop that calls your method. You time the loop, you subtract the overhead, you divide by the number of times the loop went. And I showed you how to dynamically double the amount of times the loop runs until you hit a second. Okay? That loop does not gradually increase the parameter to your method. It just increases the number of times you call that method with that parameter. Yeah?
So when we submit something to one of the quizzes on Canvas, we can't go back and look at our submissions. Is that on purpose?
Okay, Canvas is broken. We all knew this. He's asking about that you do the quiz and then you go back and you can't see your submissions. The problem is, if you go back and look at your submissions, it'll show you, if I allow that, it'll show you what's wrong. It won't just show you what you entered. It will show you which is right and which is wrong. Furthermore, I forgot for a couple days that I need to mute the assignment as well. Because I'm sure some of you found out, you can just take the quiz and go see what your grade was. And then fix your mistakes. So I remembered that. And for those of you that get started yet aren't going to benefit from that, I muted the assignment. Yeah, it's one of my many frustrations with Canvas. Yeah.
Sorry, bring this up again. I think if it's blocked on Canvas, it's not on the user side. I think you have it blocked. There's that symbol up at the top of the module. Next
Oh, the whole module's blocked.
Yeah.
Joe, that's following.
Okay. Any other questions? Yes?
Do we have to start from an n equals 2, or can we start from like an n equals to 1024? Like, is there a specification where?
Well, I mean, okay, so it's asking what size of n should you use for when you time your error, and what sizes of n. It's up to you. You're doing the analysis. Precious. Any other questions?
What do you mean by impressive?
What do I mean by impress us?
Yeah.
Do a good job. The grader should look at your solution and say, he really knows how to do timings. Okay? If on the other hand you submit something, say, okay, I timed for n equals 10 and n equals 20, because he said it was up to me, and you get points taken off, it's because you didn't impress us.
Don't you want us to do like a doubling each time or something?
You're designing. Yeah, we have expectations, but I've made them clear. I talked about how to time algorithms. Hopefully, if you don't follow my guidelines, that's not going to be very impressive. Okay? Okay, so we were in this last time. Let me get back to where we were. All right, we were talking informally about complexity analysis. And let me just repeat this. When we say that a function is O of n squared, so we have a function f of n, and we say that it's O of n squared. These are some sort of informal ways of thinking about it. This is the way I generally think about it. And this first way is, I think, probably the best. We're saying its high order term is no bigger than an n squared term. Okay? So that means you have to be able to compare terms and know which is higher order and which is lower order, but that's usually pretty easy. So, you know, if f of n equals 7n cubed, is it O of n squared? No. The high order term is bigger than an n squared term. So big O puts an upper bound, informally speaking, it puts an upper bound on the largest term in the function. Okay? Suppose you have a function that describes the distance that an object in free fall has fallen in time t. Okay? What bound could you put on that? Yeah?
The ground.
Well, the ground, yeah. But I mean, let's say it's in free fall, it hasn't hit the ground.
Terminal velocity?
Well, I use big O notation here. Yes?
Constant, because once you hit terminal velocity, it's not going to go any faster.
Okay, free fall without an atmosphere. Yeah?
It's t squared.
T squared, it's O of t squared. Now I did that example for two reasons. One is a lot of times I'll ask that, I'll say you got a function of t and put a bound on it and they'll say O of n squared. You know, if it's a function of n, your big O needs to be a function of n. If the function is a function of t, you should be talking about O of t squared. And the other is you can use big O notation to describe any function, not just algorithms. Okay? All right, so big O puts a bound on the high order term. Also, in the limit, so as we get close to, as we go toward infinity, what we find out is that other ways of thinking about it is if you double the size of the input, the value of f of n will quadruple in the case of n squared. So it puts a bound on the rate of growth. And I put various ways up there of describing the rate of growth, but basically big O puts an upper bound on the rate of growth of a function. When you say something is O of n squared, you're saying it does not grow any faster than a quadratic function. And quadratic functions have the property that if you double the input, the output quadruples. Right? Then we've got this companion notation, which is omega of n squared, which gives a lower bound. It just approaches it from the other end. It's saying that the term is no smaller than n squared. And then we've got this theta notation, which you can use. You say something is theta of n squared when it's both O of n squared and omega of n squared. Okay? So, here were some examples. So this is where we left off last time. That function right there, 3n squared plus 5n plus 3. It's O of n cubed, it's O of n squared log n, it's O of n squared. Calls all those terms, n squared, n cubed, as in right here, n squared log n is in right there, and n squared are all at least as big as this high order term, n squared. Okay? But this thing here is not O of n log n, O of n, O of 1. Because those things are smaller than the n squared term. Omega, which bounds from below, it's true that that function up there is omega of 1, omega of n log n, and omega of n squared, because all those things are less than or equal to the n squared term, which is a higher order term. On the other hand, you can't say that that thing is omega of n squared log n or omega of n cubed, because those terms are bigger than n squared. Theta, all you can say is the thing is theta of n squared, because that's what it is. Yeah?
Why is it generally used, why is O generally used instead of theta? It seems like they would...
Okay, that's a good question. Why is big O used instead of theta in most complexities? it's just sort of a long habit. I have a feeling big O was around a while before the other notations were. And big O is often used when the speaker or the writer really means theta. But I can only speculate as to why. Yeah?
But does every algorithm or complexity have a theta? Not everything does, right?
Okay, so another good question. Can you use theta notation to describe anything? Well, clearly, that function right there, you wouldn't mess around with it. You know exactly what it is. You would just say that's theta of n squared, because you can see what it is. On the other hand, suppose you're trying to characterize the running time of insertion sort. So you're trying to put an upper bound on the amount of time that insertion sort will take as a function of the array input size, and you're trying to put a lower bound on the amount of time it can take. So what is the best upper bound you could give on the running time of insertion sort? It's what?
N squared.
Yeah, it's O of n squared, because in some cases it takes n squared time. Now, what about the lower bound? It's omega of n, because sometimes it runs in linear time. So the best, when you're talking about the running time of insertion sort, you're really talking about sort of a whole bunch of cases. Big O puts an upper bound, omega puts a lower bound, and insertion sort can be anywhere in between. You couldn't put a theta bound on insertion sort there because it's not always n squared or not always n. It's just somewhere in between. Yeah.
So then you would just say that it doesn't have a theta, or it's not?
Yeah, there's no way to put a theta bound on it. You can only put a theta bound on something if you can put identical big O and omega bounds on it. Yeah.
So just to follow up with that, you're saying then that not only does the omega and the big O, they have to have one that's the same for it to be theta, but you're saying that the big O, the smallest big O and the largest omega have to be the same for it to be theta, right?
Well, you have to be able to make the big O small enough and the omega big enough so they meet.
Yeah.
If you can do that, then you can use theta notation. So for example, selection sort. When I say selection sort is theta of n squared, what am I saying? Yeah?
Upper and lower bound.
Upper and lower bound are both n squared. You take any array and run selection sort and time it. You do a timing experiment where you pick different n's. You're going to get a quadratic curve every time. If we do that experiment with insertion sort, and you graph the time consumption, you get something, it's not going to be any steeper than a quadratic, and it's not going to be any flatter than any flatter than a linear line. Okay? But you can't say for sure exactly how it's going to be shaped. Now there are two other notations that we won't use much after today, but just for completeness, it's little o and little omega. Little o is just like big O, except with big O we say, f of n is big O of g of n, and g of n is at least as, let me back up. Here we're saying its higher order term is no bigger than an n squared term. If we say little o, then its higher order term is bigger than an n squared term. So if we just struck out the no right here, take that out. Now we've got a definition of little o, an informal definition of little o. A function f of n is little o of n squared when its higher order term is bigger than an n squared term. And similarly for little omega. So for example, that function up there is not little o of n squared.
I think you got that one.
Okay? It's little o of n cubed. It's little o of n squared log n. It's not little o of n squared.
You mean it's not bigger, not no bigger? You said it's bigger, but you meant not bigger.
No. This function is little o of n cubed because this n cubed is bigger than that n squared. Yeah?
When you say higher term, do you mean the higher term of the function
Yeah.
up top, 3n squared?
Yeah.
So,
Well, in particular, I mean the higher order term ignoring constants.
right, so the higher order term there is n squared. and then going back in the slide, you'd say n squared is bigger than n cubed.
Oh, okay.
Yeah.
Stefan's right, and you're right, and everyone else is right. I was thinking, okay, I won't explain what I was thinking. It's higher order term, so the higher order term of the function is smaller than n squared.
Yeah.
Or what I was thinking was this, if you're saying little o of n squared, then I'm saying that the higher, anyway, I made a mistake. Okay, so if you want to say something is o of n cubed, it has to be smaller than n cubed. The n cubed has to be bigger than the thing you're characterizing. And for omega, it has to be smaller. The function you're characterizing has to be bigger than the omega value. Okay? So little o and little omega have to be loose bounds. They can't be tied up against. It can't be exactly the thing being bounded. And that makes it nice. That makes it nice because it gives you a perfect analogy to less than or equal to, greater than or equal to, and greater. So you say f of n is theta of g of n, then you're saying, okay, f of n and g of n have the same higher order term. Big O gives you an upper bound, possibly tight, possibly less than or equal to. Little o gives you a loose bound, has to be less than, and similarly downward. We'll stick primarily, like I said, with big O, theta, and omega. Or big O, theta, and big omega, I should say. Okay, now we're going to use our complexity notation in a variety of ways during the semester. So I want to show you some examples. So there's selection sort. And sometimes we use complexity notation to describe the running time of an algorithm or the memory consumption of an algorithm. And in this case, I want to talk about the running time of selection sort. So any bounds that you put, the upper bound that you put has to be a bound on the worst case, and the lower bound that you put has to be a lower bound on the best case. That's the convention when talking about particular algorithms. You want to put a big O bound on the worst case, on the best case, a little O bound, you want to put a big O bound on the worst case, you want to put an omega bound on the best case. And if you can do your job perfectly, ideally you'd like them to meet in the middle. That's not always possible. For selection sort, it's possible to put an O of n squared bound on the worst case, and omega of n squared bound on the best case. So you can just say the whole thing is theta of n squared. So these are all true things we could say. We can say selection sort is little o of n cubed. That leaves a lot of possibilities open, but it's a true statement. You can say it's theta of n squared, that's true. You can say it's a little omega of n, that's true. But in practice, we would just say, the most precise thing we can say is that selection sort is theta of n squared. And that one statement puts an n squared upper bound on the worst case, and n squared lower bound on the best case. Yeah?
Why are you able to do that if it has a different best case and a worst case?
Say that again. Any other questions?
Big O doesn't mean worst case.
No, big O does not mean worst case. Big O means upper bound. Okay? Now, when we're describing an algorithm, we use big O to put an upper bound on the worst case running time. Well, sometimes we use it for other purposes. It is used for expressing upper bounds. Right, so that's one example. Now here's insertion sort. Okay? In the best case, if the array is already sorted, that inner loop only runs once each time through the outer loop. And so at best, there are theta of n data comparisons. And it turns out the number of comparisons dominates everything else. So really, for sorting algorithms, we just count comparisons. And at worst, you do n squared data comparisons. So you've got theta of n data comparisons in the best case. You've got theta of n squared data comparisons in the worst case. So using our notation, how can you characterize the running time of insertion sort?
So it has a big O of n squared and a big theta of n.
It's, right, so it's big O of n squared, and it's big omega of n. That's the best you can say. It's somewhere in between, like I said earlier. So this last point, if you feel like it, you can say that the worst case is theta of n squared. We know the worst case takes n squared time, so those are true statements as well.
So you can also bound the worst case and best case. You don't have to just bound the running time.
Right, you can bound anything with, put an upper bound on any function with big O, and a lower bound on any function with big omega. It's whatever suits you. Now, it is true that insertion sort is O of n squared and omega of n. But unless we add and the bounds are tight, that might not be the strongest thing you can say. It is also true that insertion sort is O of n to the fourth and omega of 1. That's a true statement, but the bounds aren't tight. So what you want to do is put a tight upper bound and a tight upper bound and a tight lower bound. That means tight means they can't be improved. There's upper bound is as low as it can be, and the upper bound is as high as it can be. So the convention is when you describe an algorithm, you give tight bounds. Now sometimes, especially with a new algorithm, it may be very difficult to analyze. You might not be able to prove that your bound is tight. You might be able to say, okay, this is an O of n to the fifth algorithm. Maybe it's faster, I don't know, but it's certainly no worse than n to the fifth. Now what we just talked about was putting bounds on algorithms. Now let's talk about when we use this notation to put bounds on classes of algorithms. For example, sorting. So think of the sorting problem. So you often hear people say, sorting is omega of n. So when you put a lower bound on a problem, not on a particular algorithm, but on a problem, you're making a statement about every sorting algorithm. And when you put a lower bound on a problem, you're saying that every algorithm is going to be omega of n. That means every algorithm that has a name that is in a book. It also means every algorithm that has not yet been invented. Any sorting algorithm is going to be omega of n. That's what you're saying when you say sorting is omega of n. Now, why is that true? How can we prove? Yeah?
When you're sorting, you have to visit like every item.
Right. So what she said was, when you're sorting an array, let's say, you've got to at least look at every element. That'll take linear time. So you can't do better, than linear time. Yes.
So there's a kind of like a hidden assumption that we have to visit every element once. We can't just visit all of them at the same time. Or in
right. The assumption that we're making is that we're doing sequential programming. We're not doing parallel programming. Okay. So parallel complexity is a different matter. You can improve on a lot of classical algorithms by doing them in parallel, but we're sticking here with sequential algorithms. It's not hard to convince yourself that any sorting algorithm is going to have to look at every element. That'll take linear time. So that's what it means when you put a lower bound on a class of problems. Now, what does it mean when you put, let me skip over it, not skip over it. The second statement, comparison-based sorting is omega of n log n. Comparison-based algorithms are ones that the only thing they do, the only way they can the only thing they can do with the elements being sorted is to swap them around and to compare them. Can't take them apart and look at their bits. So it turns out that sorting-based algorithms are omega of n log n. So comparison-based sorting has omega n log n. You may have seen the proof of that. We'll look at it again later. So when I say that sorting is omega of n, that means that the worst case, every sorting algorithm has a worst case that's omega of n. When I say that comparison-based sorting is omega of n log n, I'm saying that Every comparison-based sorting algorithm will have a worst case that's omega of n log n.
You mean best case?
Best case.
I think I said the wrong thing before. I'm having a tough day. The worst case. Okay, think about insertion sort. Is insertion sort a comparison-based algorithm?
Yes.
Okay? Does it have a worst case that's omega of n log n? Yes.
Yes.
It has a worst case that's n squared. But it has a best case that's better. So when you put an omega bound on a sorting algorithm, on sorting, you're saying that every algorithm has a worst case that's omega of n, or omega of
The
n
worst
log n.
case is at best n log n.
What?
In other words, so the worst case is as best as n log n.
The worst case is omega of n log n. It's n log n or worse. Okay? So when you put a lower bound on a class of problems, you're putting a lower bound on the worst case of every algorithm that exists or is yet to be discovered. Okay. What does it mean when you put an upper bound? So what does it mean when I say that sorting is O of n squared? What does it mean if I were to say that? The sorting problem is O of n squared.
The longest runtime.
Yes?
Can't do worse than an n squared requested.
Depends what you mean by can't do worse. I need a more precise answer. Yeah?
It won't take any longer than n squared?
Well, okay, so it's a true statement that sorting is O of n squared. It's certainly possible, though, to invent a sorting algorithm that's worse than that. So what does it mean to say that sorting is O of n squared? Yeah?
Greater than or equal to in runtime?
No? Yeah?
Based on what you said about omega, when you say something, like when you say just sorting blanketedly as O of n squared, you're saying like all sorting algorithms are not going to be slower than n squared.
Okay, so basically when you first hear about this, you want the two definitions to be symmetrical, but they're not. Okay? Omega puts a lower bound on the worst case of every algorithm. But big O, when you say sorting is O of n squared, you're saying something different. Yeah?
You say that sorting is O of n squared, you're saying the best algorithm we have is O of n squared.
Exactly. So when I say this, the sorting problem is O of n squared, I'm saying that there is an algorithm that is O of n squared. There is a sorting algorithm that's O of n squared. You're not making a statement about every sorting algorithm the way you are at the omega bound. You're just saying that it is possible to write an algorithm that runs in O of n squared time. In fact, what's a stronger statement I can make about the sorting problem than saying it's O of n squared? Yeah?
It's O of n log n.
It's O of n log n. There are O of n log n comparison-based sorting algorithms. Now, if we take away the comparison-based sorting algorithm, sorting is O of n. Okay? There are sorting algorithms that run in linear time if you can do things other than compare the elements. Yeah?
So in past slides, you were talking about, like, when you made a statement like that, you were talking about being tightly bounded or not tightly bounded. Is that a technical term or just as long as it's...
No, tight is a technical term. Okay. Which basically means either as small or as big as possible.
So then n log n would be a tight...
Right. O of n log n is a tight bound on the sorting problem. So, yeah?
So the way that kind of just tightness and the O's are defined is you look at the limit as n approaches infinity, you look at the ratio of your function and the function inside of whatever O you're working with. Is it 0? Is it a constant? Is it infinity?
That's true, but in this case, we're putting a bound on all sorting algorithms. Then that doesn't really work because you've got an infinite number of algorithms to worry about.
Sure.
Your definition works if you're talking about a particular function.
Right.
Yeah?
Where is your for all and there exist coming from? Is it in the sentence that you're using O and omega?
Yeah, right here. I mean, when we say some problem's omega of g of n, we're saying that every algorithm for that problem has a worst case that's omega of g of n. That's just by convention what it means to put an omega bound on a problem, not an algorithm, not a function. And big O, you know, I say every shows up in that term. Some, or one, shows up in here. Go back. Okay. You know, when we say that some problem is O of f of n, we're saying that there is an algorithm that has a worst case that's O of f of n. There's some algorithm that's O of f of n. Yeah?
So when you said you want these to be symmetrical but they're not, is this what you're referring to?
Yeah,
Omega is
right.
every and then...
This lack of symmetry.
Yeah, okay.
Every and some. Yeah?
I just want to double check that for the one with omega, it should be best case.
No, the slides are correct. I was just saying, what I said was wrong for a while. Both case, it's worst case in both places. So, what's the nice thing about, you know, someone at some point proved that comparison-based sorting is omega of n log n. How does that benefit people to know that? Yeah?
You'll never waste your life looking for a comparison-based sorting algorithm that's omega of n.
Right. It lets people that research algorithms know there's not going to be an asymptotically faster algorithm than merge sort. Right? Merge sort's n log n. Heap sort's n log n. You're not going to find a linear time comparison-based sorting algorithm. Now you might find something faster than merge sort, such as quick sort, on average at least. But you're not going to improve on that n log n bound because that's just a feature of the universe you can think of. In this universe, you can't sort faster than that if you're doing comparison-based sorting. Okay? So it's important to understand when we use our notation to describe an algorithm, we're using it in a different way than when we use our notations to describe a problem. And this is what it means when we're trying to describe a problem. Okay, now in practice, when you're doing complexity analysis, you come up with some expression and you want to know, you know, I've said you can throw away low order terms. Right? You can simplify a complexity expression by throwing away low order terms and throwing away constants. And this domination is another way of defining low order terms. So one term, you know, term A dominates term B if A is of a higher order than B. So this just sort of tries to make a list of things that dominate other things. So for example, factorial dominates exponential. Any exponential dominates any polynomial. Any polynomial dominates any power of a logarithm. And then any power of a logarithm dominates constant. But even within that, there's some differences. So for example, suppose you're comparing two exponentials. Suppose you're comparing 2 to the n and 3 to the n. What does it say there on this row here for exponential? What is it saying about which dominates which?
3 to the n dominates 2 to the n.
Right, 3 to the n dominates 2 to the n. So as long as, it's only an exponential if the base is positive, is greater than 1. But the higher base dominates the lower base, as long as we're talking about things greater than 1. So if you have a measure like, you know, if you want to know the complexity of 3 to the n plus 2 to the n, you can throw away the 2 to the n because that's a low order term. 3 to the n dominates 2 to the n. It works that way for polynomials as well. N cubed dominates n squared. It works that way for logarithms. So log of n squared dominates log of n. But the base doesn't matter. Base of a logarithm doesn't matter in complexity measures, so we just leave it off. Because the difference between log base 2 of something and log base 4 of something is just a factor of 2. So, and you can throw away leading constants. Let's see if this will work here. It doesn't work. So I want to show you something about complexity. Let me go back to it's great. All right, so this is a spreadsheet. And what I have is values of n that range from 4 to 8 to 16. So that's quadrupling each time all the way down to whatever that is, 1 million or so. In this column here, I have the constant a. In this column, I have b times the log of n. In this column, I have c times the c times n. This is d times n log n. This is e times n squared, f times n cubed, and g times 2 to the n. Down here, I set the values for a, b, c, d, e, f, and g. Those are leading constants. The things that are yellow are the biggest things in their row, except I'm ignoring this column here, the exponential, because it gets out of whack so fast. You can see it's already too big to deal with in this spreadsheet. So if I make a big here, so I'm going to change a from 1 to 100. Okay? If I do that, yeah, this constant is bigger, but only for one step. Once n gets a little bit bigger, suddenly this f of n cubed is bigger all the way down. Eventually, when n gets big enough, no matter what the constants are, higher order term will become bigger and stay bigger. That's why you can throw lower order terms away. So let me make b here be 1,000. Okay? So b log n, 1,000 log n is bigger than n cubed for a little while, but then the n cubed starts winning. You know, if I make this d 1,000, same deal. You know, I could make this 10,000. I could make this, I can make it 100th. That's the idea about low order terms. No matter how you handicap the high order term, and no matter how much you advantage the low order term by leading constants, the high order term will eventually dominate. It becomes bigger and then just pulls away. And this column here with the exponential just shows you that exponentials are bad news. They get just out of hand very fast.
Where's factorial?
I didn't put factorial. It gets out of hand even faster. Okay, so that's domination. So then these are our simplification rules. We want to simplify a complexity expression. We can throw away leading constants. C times g of n is theta of g of n. So we can safely ignore leading constants. What is this thing right here saying? This is if f of n is little o of g of n, then g of n plus f of n is theta of g of n. Why are we using little o notation here?
F of n is strictly less than g of n?
Right, we're saying, when I say f of n is little o of g of n, what am I saying about f of n?
It's dominated by g of n.
It's dominated by g of n. It's a lower order term. It's a lower order term than g of n. So this is just saying you throw away low order terms. And then this one looks like a mouthful. It lets you simplify products. So it's saying, suppose the idea is you've got an expression like f1 of n, f2 of n. Well, and you got, well, let's look at this one here. You've got f1, g1 of n, g2 of n, and you're trying to simplify it. This is saying if f1 of n is little o of g1 of n, so if f1 of n is a low order term compared to g1, and if f2 is no bigger than g2, then the product dominates, the product g1, g2 of n dominates f1, f2. This will make more sense to look at an example. So rather than dwell on this, I want to show you the example. So you can just apply these rules to simplify things. Okay, how would you argue that 3n squared plus 5n minus 3 is theta of n squared? Yeah?
Because n squared dominates all the other terms.
Okay, so we are allowed to throw away low order terms, and we know that n squared dominates those lower polynomials. That leaves 3n squared.
Throw away the coefficient.
Also allowed to throw away the coefficient. Okay? How do you argue that n is little o of n log n? In other words, that n is dominated by little o of n log n. So if you had an expression like n log n plus n, it's safe to throw away the n. How do we justify that using the rules that I showed you? Yeah? Or you're... Yep.
1 is little o of log n, and using the third rule you showed us, n times 1 is big O of n log n.
Okay, that's right. I'm going to repeat what you said a little bit slower. We got the product of two things here. So there isn't anything in the table that would let us conclude that n log n dominates n. Okay, we have to use the product rule. So for the product rule, we have to have a product on the left-hand side and a product on the right-hand side. Now clear, over here we have a product. N times log n is our product. This isn't obviously a product, but we can write it as 1 times n. So think of this on the left-hand side as 1 times n. Now, what's the relationship between 1 and log n?
Log n dominates 1.
Log n dominates the 1. And what's the relationship between n and n?
They're the same.
So n is O of n. N is big O of n. So that's exactly, if we go back to here, that's exactly what it said in this third rule right here. So F1 in this case is 1, and G1 in this case is log n, and we know that 1 is little o of log n. And then F2 is n and G2 is n, and we know that n is big O of n. And that lets you conclude that the product, 1 times n, is little o of the product n times log n. So you got to be able to break it up into pieces. So it's broken up right here. Yeah?
I'm confused because we're trying to simplify, but that seems more complicated than theta of n.
Well, what I'm trying to do is I'm trying to show that this is true.
No, you're number 2.
Oh, sorry. I'm trying to show that that is true.
Oh.
Suppose I have an expression. So here's the deal. Sometimes you're faced with situations where you're not sure which is low order term. And that makes it impossible to simplify. So let's suppose that you've got some expression that looks like this. N plus n log n. And you want to simplify that. You want to throw away the low order term. But first you've got to convince yourself that n is a low order term than n log n. If you could convince yourself, you could say that this is theta of n log n, but only if you can justify throwing away the low order term. So we have to compare this term and that term using the product rule. So I'm going to rewrite it as n times 1, and I want to compare it to, actually, just to make it a little more just like the rule that we saw, right the other way. I'm going to say 1 times n, and I'm going to compare it to log n times n. And what we have to show is that this term dominates that term. So in other words, that 1 is little o of log n. And what do I have to show about the relationship between this term, these two terms?
Big O.
Right, I have to show that n is big O of n. Well, we know from our table that 1 is little o of log n. And we know that n is big O of log n. And so we can conclude that, that lets us conclude that n is little o of n log n, which means it's dominated, and we can throw it away.
So what happens if we swap the
Let me get your question.
Actually, same thing. So in that case, we couldn't swap 1 times n, make it n times 1.
Well, suppose we did. Suppose we said, okay, let's do n times 1 and log n times n. Well, you need to show that this is little o of that. It's not. It's not even big O of that. So that's, this way wouldn't give you a proof. You need to arrange it in a way that you can get a proof. You've got to break the two sides into two pieces so that you can show that one piece is little o of the other piece and another one is big O of another piece. Yep?
Just to make sure I understand this, you could not prove that n is big O of n again. You can only prove that it's little o of n log n.
No. If we know that n is little o of n log n, it is also true that n is big O of n log n. That implies that. But we're interested in the little o because we're interested in proving that this term right here, gosh, this is the one that we throw away. We want to show that this term right here dominates that term right here so that we can throw it away. You only throw away terms if they're dominated. So it lets you compare all kinds of weird things. Because the table just talks about, okay, polynomials dominate logs. But what if you got a mixture of polynomials and logs? There are products. How do you simplify? All right, let's take a break. Okay. One thing I forgot to announce at the beginning is that the consulting hour schedule is up on the help page. Stefan, does it also say where the TAs will be?
Yes.
Okay. So they won't be in a lab. They'll be in offices up in.
Is that TA room 3115?
That sounds about right.
That's what I wrote.
Okay. So that'll take effect today. All right, let's do another one of these. How can you show that n squared dominates n log n? Take a minute and do it. Talk to people around you. And use that product rule to show that n squared dominates n log n. Remember, both sides, you got to split it up into one part that's dominated and one part that's
big
upper bounded.
So we say Rn is true. And you're true or false, right? And you have and then you take
Okay, let's talk about it. Who could help me out here? How do I do it? Okay, so we're basically comparing n log n to n squared. So how do we break it down to use a product rule? Go ahead.
So we say n squared is n times n, and then we say...
Okay, so we're going to write like this.
Then we compare log n with n.
Okay, so we know that log n is O of one of those n's.
And n is big O of n.
And the other n is, and the n is big O of the other n. So that satisfies, that shows that we can break the left-hand side up and the right-hand side up into two pieces such that we've got these two properties. And that just lets you conclude that n log n is little o of n squared. In other words, n log n is dominated by n squared. Matter of breaking things up. Yep?
Is it okay to think of the statement log n is little o n as saying log n is less than o n, and then saying saying.
Well, it's wrong to say log n is less than n because it's not true for all n. Right? It's bigger than it for a while. It could be, depending on leading constants. It's just best to say log n is dominated by n, or little o of n. Yeah?
Could you say that the asymptotic growth of log n is less than that of n?
Yes, you could say asymptotically log n grows slower than n. Yeah.
Could you divide one by the other?
He's asking, could you divide one by the other? Sure. You could take, I think someone mentioned that before, you could look at the quotient and look how the quotient is as it tends toward infinity. So if the quotient is a constant, then it's the same asymptotic complexity. If it's
less than or equals to 0.
Yeah. It is a 0, infinity, or state constant.
Can we take the derivative?
Well, let's not get into that. Okay, any other questions about that? Let's see what else is on this slide here. All right, so that's what we just said. Log of n is little o of n, and n is big O of n. Okay, try that one. 100 times 2 to the nth power is little o of n times 2 to the nth power. Notice that n right there is insignificant compared to 2 to the n. But is there enough of a difference to make it so that n 2 to the n dominates 100 2 to the n? So we're going to use the product rule again. How do we split it up so you can apply the product rule? Okay, got an idea?
Yeah, so you can split the left-hand side up into 100, which is a constant.
Mm-hmm.
And so any constant is little o of n.
Okay.
So splitting the right-hand side up, yeah, and then 2 to the n is big O of 2 to the n. So.
Right, so we get 100 times 2 to the n on this side, and we got n times 2 to the n on that side. 100 is little o of n. 100 is dominated by n. 2 to the n is obviously O of itself, big O of itself. So you can apply the product rule and conclude that this is little o of that. Any questions about that? Now, we get into the exact definition of asymptotic complexity. So generally, we just think about, okay, here's an expression, throw away the low order terms, get rid of the leading constant, done. But it's good to know the exact definition. And I'll start with the book definition. The book definition says, it's trying to define when f of n is O of g of n. And it says, let f of n and g of n be functions from positive integers to positive reals. So it says that f of n is big O of g of n if there is a constant c such that f of n is less than or equal to c times g to the n. That's non-traditional, and I find it hard to work with. So we're going to use a more traditional definition, which is more complicated, but it turns out to be easier to work with. So what it says here, we got f of n and g of n are functions from reals to reals. So the first one was just talking about integers, positive numbers first of all, and for integers to reals. So in the second definition, n can be any real number. So we say that f of n is O of g of n if there are two constants, c and m there, such that 0 is less than or equal to f of n is less than or equal to that constant times g of n for all sufficiently large n. Okay? Now that's, they're equivalent as long as you restrict yourself to positive integers to positive reals. Let me draw some graphs and let's talk about, let's just see what the idea is behind those definitions. So we go back to this. And I will save it in case I want it later. And so let's consider a function like, this function here, let's say it's like 5n. And then we got a function like, these probably not to scale. There's n squared. And we're claiming that 5n is big O of n squared. So how do we use the formal definition to prove that 5n is O of n squared? What is it that the definition is saying? Yeah.
Pick some coefficient c and some minimum n, and show that any n greater than that n, for any n greater than that n, c times n squared is greater than 5n.
Okay. So we just pick a constant. In this case, I'm going to let c be 1. I'm going to let c be 1. So what we're comparing is literally the curve 5n and the curve n squared. Normally, you get to multiply this thing by a constant. We'll just let the constant be 1. So what we're looking for is a place down here, which we'll call n naught. And it has to have the property that beyond this point, this function is bigger than that function. So is there a point where the n squared curve crosses the 5n curve and stays above it forever? Okay? If so, then we have proven it. We have found a constant. We'll multiply n squared by 1. And we will ignore small numbers. And we just need to find out, where is it? What is that point? How could we find that point? Yeah?
Set 5n equal to n squared, and then solve for n, and any n greater than that.
Right. We know that the n squared is eventually going to catch up and cross. We just have to show. So n squared equals 5n. That gives us n equals 5. So at n equals 5, we'll let that be our n naught. N naught equals 5. Both functions have a value of 25. Beyond that point, the n squared will be bigger. And, another way to look at it is just look at, we want n squared minus 5n to be greater than 0. And we can divide through and we end up with n has to be greater than 5. So that's the whole game. To formally prove something is big O of something else, you've got to find a number to multiply one of the terms by, and then a point where you start carrying. So n0 could be anything bigger than 5 as well.
Well, couldn't n0 just be 0 and then just multiply n squared by some big number? Or, I mean, n not be 1 and then
yeah, I mean,
it has to be some big.
Yeah, in this case, let's see, what would it work to let n naught equal 0?
Not 0, 1.
Oh, let n naught equal 1 and let c equal 1,000,000.
So 5.
Is 1,000,000 n squared bigger than 5? Is 1,000,000, okay, let n be 1. Is 1,000,000 is bigger than 5?
Yeah.
And it's not going to do. So yeah, that would work as well.
So
typically, the bigger you make the constant, the further to the left you can put the n naught.
So the c is arbitrary.
It's arbitrary constant. To prove big O-ness, you have to find a c and an n naught. And here I've gotten a couple. Right? Here, the first place I use c equals 1, n naught equals 5. He suggested c equal 1,000,000, n naught equals 1. Lots and lots of ways to pick these numbers. Yeah.
Is c not multiplied to both graphs?
No.
Okay.
You just multiply the. We're trying to show that 5n is O of n squared. So the constant is used to multiply the thing, the big O term. Yeah.
Can you go back to the definitions?
Yep. So here's the definition. So we want to, f of n is big O of g of n if there are positive constants c and n naught, such that 0 is, first of all, f of n has to be positive, and it has to be less than or equal to c times g of n for all n that are greater than or equal to n naught, for all sufficiently large n.
Fn is just equal to or greater than 0.
Okay, not pop, yeah. F of n has to be non-negative.
So what if we want to use the book definition instead of the more traditional definition? Would it still work?
Yeah, okay, so he's asking about what if he wants to use the book definition. It works as long as you're only talking about functions from positive integers to positive reals, which we typically are. But it's a little bit hard to work with because suddenly you're not talking about continuous functions anymore. You're talking about integer, functions where the domain is integers.
Because you can have 0 in some cases.
Yeah, it's just, you have to trust me that it's easier to work with the non-big definition. Okay, so let's look at an example here that I already have cooked up. F of n, which is the blue curve, is 1 over n plus 2. G of n, which is the pinkish curve, purplish curve, is g of n equals 1. So, how would you argue that f of n is O of g of n? Or could you? Could you argue that f of n is O of g of n?
Yeah.
I've got one yes so far. What do you think?
For positive integers?
Is the blue curve O of the pink curve?
Oh. For positive integers?
Now I've got a no. No,
for positive.
Yeah. Right here.
Yeah. For positive n.
Yeah. What's your thought?
I think we can prove it by setting C to be greater than 2.
Okay, so let's let C be 3. What does that do to that pink curve? If we multiply the pink curve by 3.
Moves up.
It moves up to here. Okay? Now, it crosses it at some point. Is it going to stay above it forever?
Yeah.
Right, yes. So we just have to pick a C. So let C be 3. How big does n naught have to be?
1.
I don't know if 1 will work. I'm pretty sure 2 will work, though, because that's where I am right here, right? I'm not sure where 1 falls. Let's see. 1 over 1 plus 2 is 3. Yeah, it's sort of tied right there. So, yeah, 1 would work. But anything greater than or equal to 1 will work as an n naught. So you're allowed to ignore small order terms, basically. And you ignore you look at the big order terms. So you can throw away small numbers. You just want to know what happens in the long run. And yes, this eventually becomes bigger and stays bigger. What about the other way around? Can you show that the pink curve is O of the blue curve?
And equals 2 and
Well,
C equals 1.
You can let n equal 0 and let C equal 1. You don't have to do anything to the graph because that blue curve will always be above the pink curve. So you don't have to advantage it with a constant. You don't have to throw anything up. So they're theta of each other.
So you mentioned earlier that n has to be a positive integer. So does 0 count as a positive integer?
No, 0 is not a positive integer. Now, I'm not going to dwell on this. So this is what we just talked about, the formal definition of big O. There are also formal definitions for the other things, but let's just stick to big O. If you can understand the big O definition, the rest is just more of the same. So, I want to prove that 5n squared is big O of n squared. And there's my proof up there. So what's the idea behind the proof? You've got an n squared curve, which is right here. You've got a 5n squared curve, which is right there. Yeah?
We could set the green curve as our g of n and set a constant.
Okay, what constant would you use?
Greater than
We got to find some constant that eventually, for large enough n, brings this green curve at least up to the red curve.
6, right?
6 would work, or 5 would work.
Oh yeah, since it's less than
All right, we multiply the green curve by 5, you've got 5n squared, and now they're exactly the same for all n. So you can use any n naught, constant of 5. So if I multiply by 5, oh, never mind that. This is another proof. Okay? Now what about this? I want to show that 5n is O of n squared. This is similar to the example that I sketched for you.
N greater than.
I mean, we can see right here, that's where they cross. So we can let constant b1, leave the green curve unaffected, and n naught of 5, and from that point on, the green curve is bigger than the red curve. There's no need to multiply the green curve by anything. Yeah?
Sorry, I'm just a little confused on like the previous example, why picking a constant that is greater than the constant 5, like, how does that prove anything?
The definition of big O says this green curve, the red curve is big O of the green curve if we can find a constant to multiply the green curve by, and a point on the x-axis such that the scaled green curve is at or above the red curve for all numbers to the right of the point we picked. If we can find those two constants, then that does the proof. That's just the definition. For sufficiently large numbers, there's a way to scale the curve so it's above the other curve. The same thing here. So you can solve for these things, or you can just sort of guess at them. Yeah?
Right, so basically this is just like the written proof of the like short rule that we were talking about earlier, that the leading constants don't affect, right? Is
right.
Correct?
No, this you can show why leading constants don't matter, because suppose we change this and we made this 100 times, 500 times in instead of 100 times in. No leading constant is going to screw up the proof, because we can just make the constant look like n squared by bigger.
Right. Okay.
No matter how steep this line is, you know, we can find a place where this thing catches up and passes it. Okay, what about that? So now I've got log 2 of n, which is the blue curve, log base 2 of n, and I've got log base 4 of n, which is that curve. And I want to show that log 2 of n is O of log 4 of n. This curve is big O of that curve.
So can we just do log 2 of 2 divided by log 4 of 2?
Well, let's look through it here. There's a way to convert between bases of a logarithm, and it turns out that if you do that, you'll find that this curve is exactly twice this curve. That's what we're doing in symbols up there. Okay? So if we multiply the red curve by 2, what are we going to get? I keep thinking I have an animation, but I don't. Yeah. If I multiply this curve by 2, I get the blue curve. And so a constant of 2 or bigger, C of 2 or bigger, and any n is going to complete the proof.
Sorry, so quickly, so shouldn't n0 be 1 in this case? If C is equal to 2?
Okay, so he's saying shouldn't n naught be at least 1. I'm ignoring the other part of the proof. I've got to find an n naught not only where this red curve scaled by a constant is above the blue, but I also got to make sure that it's not negative. So I've got to pick an n naught that's at least 1 to prevent having, because the curves go negative right here. So I forget that because that's usually is not even an issue. But yeah, you got to put a bound that's big enough to ensure that the function's at least positive. Yeah.
It almost looks like it's enough to display the graph because the red line is less than the blue one. Right?
No, but I was showing, if I was trying to show that the red line was O of the blue line, yeah, the graph establishes that. I was trying to show that the blue line is O of the red line. And that's possible because they just differ by a constant factor of 2. Okay. What about this one? N squared plus 5n, which is red, and n squared, which is green. I'm trying to show that the upper curve, the red curve, is O of the green curve.
So the constant would be like 10 and n be greater than 1.
Okay, well, you can see, it might, let's go, let me just write through this instead of, it's sort of a dense bunch of symbols. Let's go to my other mode and try to solve it ourselves. So, let me save it. Okay, so I have this plot here. So I had the n squared term, and then I had one that was, what was it, n squared plus 5n? And I want to show that n squared plus 5n is O of n squared. In other words, I'm justifying throwing away the lower term. Okay? So if you have to approach this problem, basically you want to think, okay, I need a constant I can multiply n squared by so that it eventually crosses over n squared plus 5n. So how would I solve for that?
And set them equal.
Well, or another, I want Cn squared to be greater than or equal to n squared plus 5n. For n greater than or equal to some n naught that we got to find. So we got to find an n naught, we got to find a C that will make this statement true. So let's just simplify what we got here. Let's divide both sides by n. So we get C times n is greater than or equal to n plus 5. And what can I do next? We also got to have this. I always forget about the other part. This has to be greater than or equal to 0. How can I simplify that further?
Bring the n plus 5 the n to the other side.
Okay, so I get C minus 1 times n has to be greater than or equal to 5. I do that right? And then I'm just going to, having said it, I'm going to ignore the greater than or equal to part. Might be better to deal with that separately. And then I've got to have n is greater than or equal to 5 over C minus 1. So that one right there, we've got to find a C and an n naught. So at this point, we can just pick a C. Now, this right in here needs to be positive. So what can we pick as C?
6.
Let's let C be 6, and that tells us that if C equals 6, n has to be greater than or equal to 5. So we let n naught equal 5.
1.
You have 6, 6.
All right, I'm glad you're all paying attention. So if we let C be 6, we can let n naught be 1, and we're okay. Now what if we didn't want to use 6? What if we want to say, okay, let C be 100? Then we could let n naught be as small as 5/99. It doesn't matter. You just got to find two constants that work. Yeah.
Can we choose n naught first and then solve for C?
You could choose n naught first and solve for C, but you might choose it too small. You got to at least pick an n naught that makes everything positive. You could pick a C and try to solve for n naught, but you might make C too small. It doesn't matter how you do it. You just got to arrive. Once you come up with the answers, you got to make sure they work. Plug them back in to see if it still works. Okay? Looks like class is over. So see you later.